Now for tangent lines and derivatives, calculus style. So tangent, the word tangent is actually an adjective, and it describes a line that touches a shape in only one location. So you can see by the graph here that this tangent line here is only touching this circle here in only one location, and that is here. Notice the line does not go through the circle. It only touches the circle on an edge and then keeps going. And it is only allowed to touch in one spot. That's it. If it touches more than once, it's called a secant. Alright, so how are we going to find the tangent? Now I'm using tangent as a noun, and that's okay because that's how it's frequently referred to. And by find the tangent, I mean find the tangent line, which means I'm looking for an actual equation. Now, since I'm looking for an equation, easiest way to do that is going to be slope-intercept form. That's going to be the end goal here. So to start, in order to get the end equation, the tangent line equation, I'm going to need to find the slope first. So if you remember from Algebra 1, slope is equal to y2 minus y1 over x2 minus x1. So I have these 2 points here that are on this graph, point A and point B. Each of them have a different coordinate. My x value for point A is the lowercase a, and my x value for point B is a plus e. Now, what is e? E refers to this little gap right here between a and a plus e. I don't really care how far e is, as long as I know it's some distance away from a. This goes back to kind of that approximation deal that we did with the limits before. Also, you should note that point A is going to have a different y value than point B. Therefore, I'm going to say that point B has y2 and point A has y1. And I'm going to leave it at that for right now. So now to change this into calculus terms, I need to change my y2 into function notation. So that's going to be the function value at a plus e, and change y1 also into function notation, which would be my function value at point A. And then x2 minus x1, x2 is a plus e, and x1 is a. Cancel out everything that I don't need, which in this case means only the a's on the very bottom of the function. And I have the function value at a plus e minus the function value at a divided by e, which is the distance between my two x points. Now I can't finish finding my tangent line without finding an equation for it. So I'm going to use point slope form, which is also from Algebra 1. And this is y minus y1 is equal to the slope times x minus x1. So as you can see, everything actually has its origins in Algebra 1. We are just, you could say, revamping it so that we can use it in calculus. So now to find an exact slope. The slope before gave us the slope at A and B for the secant line, but now we need the actual slope for the tangent line, which would be defined as when A and B are almost right on top of each other. They can't be exactly right on top of each other because then it would just be point A. So we're going to define this as a limit. And we're doing it the same way that we did before. We are starting with the definition of slope. And we are saying that this little gap right here that we called E before, E, there we go, is going to be defined as going smaller. That gap is slowly going to disappear, and that's where we're getting our limit. And so to find the slope of our tangent line, we are going to use the limit as E goes to 0 of f of a plus e minus f of a divided by e. Now I will replace these with x's in the example, so don't freak out when you see them. Alright, so our example. f of x equals x squared minus 1. Oh, sorry, plus 1. I forgot what I was doing. So first I need to find my slope, which bet you never found the slope of a parabola before. So I'm going to start with my delta x. So in other words, my e from the previous examples has to be going to 0 for my limit. And this is going to be f of x plus delta x, which I've already substituted in inside the parentheses. And it needs to be minus my original f of x, which I've already substituted in as well. This total will be divided by delta x. Now, going ahead and distributing everything, I have x squared plus 2x delta x plus delta x squared plus 1. And then I distribute the negative sign into the second set of parentheses for f of x. And this is so I can do my cancellations. So you can see my x squareds will cancel out and my 1s will cancel out. And then I'm going to divide this whole thing by delta x. Now, as you can see, my only two remaining terms also have delta x's, so I can cancel a delta x out of each of those remaining terms. Notice I'm still writing limit as delta x goes to 0 each time because I've not actually taken the limit yet. So rewriting it, I have 2x plus delta x, take the limit, and I end up with 2x. Now let's say that we are going to use an example point of 1, 2 from the function. So I have y minus 2, because that's our y value, equals 2 times 1 times x minus 1. So that gives me y is equal to 2x minus 2. My negative 2's cancel out, and I'm left with y is equal to 2x. Now, why did I use this 2 minus 1 right here? Well, it actually comes from this 2x right here. I had to pull the x value from my example as well so that I could plug in to my slope. So since my slope is defined as 2x, I had to use the x value of 1 in order to get the correct answer. Notice I did not use the original f of x. Again, I am using just the slope-intercept form. Alright, that's it. Quick introduction. I will work more examples when we look at this in class. See you later.